hello everyone, and welcome to, we were trying to figure out the week number. It's somewhere 12 or 13, somewhere around that, of WESTalks. So thanks everyone for coming today. As we've heard for every week, IC Impacts is Pan-Canadian Council, Canada-India Research Centre of Excellence, which serves on a new model for international collaboration and developing research solutions to solve global challenges. It's like 7 years old now, and it's hosted here at UBC. And the UBC Future Waters is a new UBC Research Excellence Cluster on the future states of water. And we do a lot of work with interdisciplinary research at the intersection of law, policy, and governments, and applied and biophysical sciences. And we actually yesterday had our first student council, Future Waters Student Council meeting. So if you're interested in joining that, please do email me. Okay, and here's the organizing committee for WESTalks is Abhishek, Fuhar, Jaskaran, Furia, and myself. Here's the fall lineup. Last week we had Dr. Boya Zhang from MIT and University of Minnesota now. And this week I'm happy to say that we're having a presentation by Dr. Bernhard Truffer from Eawag on the sustainability transitions in the urban water sector and the promise of modular technologies from a socio-technical perspective. I'll also mention again, if you missed any of the back talks, and also we record all the presentations, so this one will be up there in maybe a day or two. So previous WESTalks are all available on the IC Impacts YouTube channel. So if you just YouTube IC Impacts and then you go to the search and you search up WESTalk here, you can see all the past WESTalks there. And we actually do get a good number of views on those. So that's great to see people are going back. All right, and now it's my pleasure to introduce today's speaker, Dr. Truffer. So Dr. Bernhard Truffer is the head of the Environmental Social Sciences Research Department at the Swiss Federal Institute for Aquatic Science and Technology, or as we know it, Eawag, in Switzerland, and a professor at the Copernicus Institute of Sustainable Development in Utrecht University. His experience is on sustainability transitions in infrastructure sectors such as urban water management, like we're going to hear about today, electricity, or transport. In particular, he focuses on the geographical conditions of these transitions in specific regions and countries, but also at a global scale. And with that, I'm going to pass it over to Professor Truffer. And I'll also mention, if you have any questions throughout the presentation, feel free to type them into the chat box. And we'll kind of compile all those. And then at the end of the presentation, we'll have the 15-minute question period. So I think I've stopped sharing. So perfect. I'm going to mute myself and let Dr. Truffer take it away.
Thanks a lot, Carl. And do you see my slides?
Yeah, we see the whole PowerPoint. Yeah, yes, there you go. Perfect.
The presentation mode. Yeah, thanks a lot for the nice invitation. And I'm really thrilled, and but also it feels a little bit creepy to have a presentation with all across the globe, you know, and not seeing people and not knowing people. But I will just try to do my best. What I anticipated could be sort of interesting for your context, you know. So I would like to introduce you very quickly and shortly, of course, into the field that I have been working on for the last 20 years or so, which is the sustainability transitions. And by that we mean fundamental transformation of sectors in over decades even, and potentially those that leads to more sustainable outcome in the end. And here in particular, I will focus on potential sustainability transitions in the urban water management sector, and in particular, the promise of modular technologies. And by that, by modular technologies, we mean like rather small scale, mass-produced units of water treatment, which might ultimately contribute to a more decentralized or hybrid structure of urban water management compared to what we know by now. So I have to be extremely selective, of course, and so I will just introduce you to very superficially to the thinking of socio-technical transition studies, and then show you why, you know, we should, or urban water management is sort of a potentially interesting candidate for this kind of research. And then I have to select only the economics part of this, you know, an argument about how quickly such a transition could happen from a purely cost competitiveness point of view. There are, of course, others, but which I cannot touch upon, but I hope you will get sort of a feel for the kind of dynamics that we have to accommodate for. And then I will do this, show you some, or walk you through some economics, engineering economics arguments about these transitions dynamics. And first, let's say in a rather abstracted greenfield examples, and then add in a second point a little bit more reality to it. And then finally, try to assess whether, we should prepare for a transition or whether this is something that is not really relevant over the next 10 or 20 years. So let's say the socio-technical transition studies is a field that has emerged like almost 30 years ago, and is sort of an interdisciplinary field among several social sciences, among which are like the history and sociology of technology. There is such a field, also industry dynamics and economics, or economic geography. And they have just started to try to understand how long-term transformations in central sectors like infrastructure sectors or others happened in a historical timescale. And they came up with lots of insights, of course, over these 30 years, but let's say the core tenets are that technologies and rules, or we call them institutions, the rules of the game, the way that people deal with it, they regulate technologies, etc. And they develop into sort of configurations that work. And by this, this means to say there's nothing like first you have a perfect technology and then sort of society adapts to that. And it accepts the technologies. And it's also not the other way around, that you first have some mission to the moon sort of policies, and then whatever technology is necessary will be developed. But in general, you see that both the rules and the technologies, they have to accommodate to each other. They have to sort of co-evolve over time. And once the configuration works, both in technical terms and in social terms, you have such a configuration that works. And this is then also very stable and creates lots of path dependencies. I will illustrate in a while. As a consequence, if you look at the longer term developments in major sectors, you can observe that there are sort of long periods over 30, 50, 80 years, where you only can observe incremental changes in these social technical configurations. But then they're interspersed by sudden bursts of revolutions and radical transformations. And in biology, they call this like punctuated equilibria. And we see sort of similar time patterns also in these longer term developments. One of the most well-known frameworks is the so-called multi-level perspective, which was developed by historians of technology. And they identified like 3 core concepts, and you should try to remember the 3 labels because I will come back with them, but it's not rocket science. You can understand that very quickly. So the regime is sort of the currently dominant and established socio-technical configuration. So in urban water management, it's the centralized sewer, it's the centralized water treatment plant or wastewater treatment plant, the sewers, etc., with the according regulatory institutions, the way that users use it, etc. But at any point in time over history, besides this regime, which covers mostly like 99 or 95% of all the services that are delivered, you always find alternatives that don't fit so well in many respects with these dominant technologies or the dominant setup, and they are called niches. And they normally need to, in order to survive and prosper and further develop, they need some protection by special, let's say, government programs or by specific companies or NGOs or whatever. And the third thing is that, let's say, over time, of course, these regimes are embedded in or exposed to broader forces, which then, put some pressure on the regimes to change over time, or might even promote niches at the expense of the regime. So let me just illustrate very, very shortly a historical example, or the poster child of all the transition studies or processes, which was the rise of the automobile in the beginning of the 20th century. So the regime in those times was horse carriage based transport of people and of goods. and you had a whole structure like, blacksmith and horse breeders and stables that were constituting this industry, and you had certain user patterns and preferences to travel in certain on the back of the horse, etc., etc. So it was quite clear how to organize that. But then around the end of the 19th, beginning of the 20th century, there was a new sort of technology was arising, which was called the automobile, which essentially meant in those times it's a horse carriage without a horse. It can just run without being, torn by a horse. But they came in different variants. There were vapor-based. I just pointed at the vapor-based solutions. Like here, which were of course dangerous, but then the internal combustion engine based on gasoline, which was also very risky to travel with, and also electric vehicles were there. Then I could go into depth what happened and how these alternatives fought among each other, and how, let's say, the internal combustion engine eventually gained predominance, and how they substituted the regime of the horse carriage. But we know by now, since more than 100 years, that the internal combustion engine won out, and that the infrastructure adapted to it. There were paved roads, etc., gasoline stations, codes of conduct, learning programs for users, etc., to stabilize, this internal combustion engine-based vehicle, and when made it to a revolution in people's transport. What you then observe once a regime is established, the variation of this basic configuration is rather marginal. So here, as an illustration, I always put the degree of variation of subcompact cars among the different automobile companies. And you see that they all look the same, essentially. They have a little bit more of this and that, but there's no radical deviation from that pattern. So let me just provide you with one sort of more abstract and schematic representation, but which summarized the thinking quite well. So let's say in the beginning, you have at a certain moment in time, this is a time dimension, the x-axis, of course, and you have sort of a configuration of technology, infrastructures, but also culture, symbolic meanings, industrial networks, specific forms of knowledge, policies, and even markets and user practices that are sort of aligned to each other so that everything fits and can grow. And they can stay really pretty constant over long periods of time. They are exposed to specific landscape pressures. They have to respond to them. They can be challenged by the technological niches, but normally they remain rather stable. So, and then you observe like short periods of time where suddenly reconfigurations happen, where sort of the niches start to grow and expand and scale, where perhaps the certain landscape pressures get more important, and there's sort of an agreement that the prevailing regime will not do it. And eventually you end up, let's say, in the automobile regime where you have the same elements, but they are arranged in a different way. So that's in a nutshell how social scientists think about these sort of long-term transformations. Well, is this relevant for urban water management? Well, first of all, we can say we can identify these concepts, like the regime of wastewater treatment can very clearly be described. So it has also been a huge success over the past 50 or even 100 years, So it's based on a centralized treatment and long-distance transport. And if you look at the innovations that happen, they're mostly incremental. So here you see the diffusion case of treatment steps in a centralized wastewater treatment plants, etc. So it's all going very smooth, and eventually, in some countries at least, like quite a number of countries in Western Europe, you reach then connection rates of above 97%. So there are some disruptive alternatives emerging, like recycling showers, waterless washing machines, or independent flush toilets that have been developed. They're still too expensive, they're not fully functional, but they are typically what you would expect to emerge as niches. And you have, of course, landscape pressures because of climate change, and also one of the major deficiencies is the limited diffusion of centralized sewers in large parts of the world, and even no real prospects that would change anytime soon. So how can we now think about these sort of transformations, fundamental transformations, and how can we assess whether there's anything likely to happen here, and whether we're at the end of an era, with our centralized way or perspective on urban water management, and whether something radically new is at the horizon. And finally, if this is the case, how we could prepare for that. Okay, this is, of course, as you might anticipate, this is sort of a big question because it has so many aspects. There's political aspects, there's preference aspects by users, etc., etc. And I, obviously, in the 20 minutes, I have to focus on one aspect, and I just focus, as I announced, on the economics dimension. And I would just show you some of the instabilities, and I would safely estimate that most of the engineers in the field, they believe like urban water management is a very stable technology and a system that will not change anytime soon. And I will try to convince you of the opposite. So the question is, how quickly could the transition in urban water management happen? And let's say to start, we had a rather simple question that we wanted to ask. So if we were in a green field and we were a dictator, that could just do the check for the benefit of the people in the region, and we would have to serve the region or the catchment by wastewater treatment systems or services. So the first thing would be we would opt for a centralized wastewater treatment plant, and the economics of that look approximately like that. So the so the cost per capita in years, so wastewater treatment plant gets cheaper per capita the more people you can connect, so up to 100% of the people living in the catchment, whereas the sewers, they tend to increase because it gets less dense towards the fringes. So the total costs are the sum of these two. If you look at decentralized technologies, so let's say these sort of boxes that you could put into your cellar or basement and which sort of work independently, you have a rather stable cost because they cost the same for each household. That you don't have economies of scale at the level of building bigger plants. But at very low densities, of course, the servicing and repair and regulation gets more and more costly because some service people have to drive around. And we have one paper where we looked at that and found out that it's very solidly, you can represent this as a sort of a hockey stick curve. So now the question of the benevolent dictator, that was the term I was searching for, would be to say, oh, let's just implement the optimal degree of centralization so that the overall costs are minimal. So you have to say like 100% of 0% of centralized treatment means 100% of decentralized treatment. And so you can just switch this, the decentralized cost curve around, and then you can derive a sort of an average, total average cost, which has some interesting points. So one, inflection points or meaningful points, so in countries like Switzerland or Austria or the Netherlands or the UK, you have sort of mandatory connection rules. So if below a certain per capita cost, you're forced to connect to the centralized sewer. And this means, of course, that the current regime point leads to a high percentage of connection, but also rather high cost on average. But there are other interesting points, and in particular, the lowest point of the curve is sort of the optimal degree of centralization, or the optimal degree of decentralization. And so we would expect that we pay too much for our urban water management system, and we could have it cheaper in total costs to deliver. So the question is, so how much cheaper would it be? Can we sort of assess the dimension of this? And so we run a sort of a greenfield model calculation in the context of a PhD project, where we took an existing settlement in Switzerland, and we sort of started to build up, if there had been no urban water management system, to build up from very decentralized structures to increasingly centralized structures, networks, and then estimated the costs of the overall system across this gradient. And we applied this to a specific region in Switzerland, central Switzerland, with 25 communities. And very quickly we found and it's a sort of a mountainous region with some urban centers. And we found there are three types of cost curves. The first one up here is really the mountain villages, where of course, you know, you have very extensive sewer networks and it gets very costly, and you have some centers, and let's say the optimal degree of centralization would be around 50% perhaps. The other extreme is here, like, you know, you have the urban center, where of course, you know, the decentralized system or the centralized system is sort of cost competitive all along. But we have quite a sizable segment in between, where we have a sort of a different cost curve, and I highlighted it here in yellow, where you see that the cost is quite flat from, let's say, almost 100% to 0%. And this means, you know, the actual optimum will depend on the costs that the actual market prices of these modular systems. And if they decrease substantially, you could really have a switching point where, you know, people would be happy with being 100% connected, but a few years later they would say, oh, what are you doing? You know, we could have a much cheaper alternative by turning everything into decentralized. So of course this is highly sensitive to cost assumptions, but let's say this flat middle range, this is something that's really discomforting, because at least in substantial subparts of an urban water management catchment, you could have a strong incentive to disconnect. And as you know, if you disconnect too many from the centralized sewer, you get all sorts of also technical problems that pursue. Very quickly, so I don't take too long, but you know, just to walk you through a little bit more. So that we did this research like almost 4 years ago, and then people said, yeah, sure, that's all very hypothetical. You know, we don't have so many greenfield situations really. And so the problem is more like if you have some costs, you know, in the sewers in particular, and they have a lifetime of 80 years, you know, this will all level out, and it will not be that dramatic. And of course, you know, so what we did is that we did a sort of a calculation of sewer systems of villages. So one case here was a mountain village with lots of long stretches, you know, and you see the red parts are the private connections, and the green ones are the public ones. And a second case where we had a sort of a suburban area with single family houses with the sewers and everything. And so for these two cases, we had also the age of the sewers, the expected lifetime there, and all the costs, you know, that you would have in your books. And the question was, if we start, we calculate over 70 years in sort of 10 years time slices. And at each point of these 10-year time slices, we decide whether we will get rid of one trunk. You know, if it's less costly to serve all these users here, with decentralized options, we will just not invest into renewal of this trunk anymore, and then all the way back, and we will see how far we will get. And this is, in a nutshell, the result of these calculations. So the red curve is for the mountain village, and the gray one for the suburban context, and the x-axis is the costs for the modular alternatives, and the y-axis is the eventual market share of the decentralized options. And what you see here, the red line here, depicts a sort of the cost, the reference cost that we calculated for current decentralized wastewater treatment plants. And they are, you know, if they are applied, then you will get like 20% of the village, of the mountain village, which gets decoupled, and let's say about 5% in the suburban area. Compared to the current connections, still like doubling or even more of the market, but still it's rather low levels. But what you have to understand is that you know, we had the total cost of such a machine was calculated by the actual cost that you have for purchasing this machine, and then opportunity costs of about 7,000 Swiss francs for putting it in your basement, assuming that people, you know, have other ideas about how to use the surface in their basement, and over 70 years you accumulate the costs of not having a place to put your bicycles, but yeah, you have your wastewater treatment plant clogging your part, you know, a few square meters of your basement. If you say, well, people don't care so much, then you will get to the dotted line. And this means already that in the Alpine region, you will already have a 100% switch to decentralized technologies and about 20% in the suburban area. So let's say, so the speed of the transformation, you know, we calculate over 70 years. Of course, this depends on the existing sewer lines, and the older they are, the quicker it will happen. Yes, so, but essentially, I guess in a qualitative terms, we get sort of a similar picture that there are sort of switching points in the development, and only the big difference is that the transition is sort of slowed a little bit. Let me now do the last part of my argument to say, well, now we also have to look at it in more dynamic terms, but because these were sort of a rather static comparison of costs. And here we have to understand that modular technologies, they have a different industry logics and manufacturing logics than centralized sewer systems. And this is they can profit from economies of scales, not at the level of the plant, like the centralized ones, but at the level of production units, the number of units produced. So they have so-called learning curve effects, and they, you know them from washing machines and TV sets, etc. So a modular system is more like a washing machine than like a bridge, you know, and a centralized system is more like a bridge and not like a washing machine. And just to illustrate what these learning effects could look like, it's very useful to look at, for instance, at solar PV. Since the end of the 70s to today, the costs of per kilowatt hour produced have decreased from $5 a kilowatt hour down to, let's say, 10 cents. And so you see dramatic 97% decrease in costs. That can happen in these sort of mass manufactured appliances or technologies. Of course, you know, modular water technologies are not solar PV. They have it's a different beast. But from our calculations, we believe that 30% are cost reductions from today's costs are very well feasible also for the modular water technologies. But just to illustrate what this means, you know, this is sort of a back of the envelope calculation that we did rather early on. If you say this is the region, the urban region of Zurich, with above that's sort of the CBD, if you want, the central area, and here you have the suburbs along the lake of Zurich. And the red colors is what we calculated, you know, from with a geographic information system approach, is probably sewered centrally, and the green ones are those that are probably sewered by decentralized technologies from a cost perspective. And you see the current situation with 2.5% market share looks all red, of course. If we take the current market prices, so you see already that quite a large area could be sewered, treated rather, by decentralized technologies. If you assume like 10% of cost decrease, it gets greener. And finally, if you are like at 25% cost decrease, you really have sort of central city, which is still centrally sewered. And most of the other areas are just serviced by modular technologies. Important fact also that if we get to that point, then the market share or the market volume of modular technologies compared to today increases by a factor of 200. So it becomes certainly a business, you know, it becomes interesting for big industry, and you will have professional operation and maintenance concepts, etc., etc. Of course, you know, these are all calculations, and they are based on very many assumptions, of course, and the likelihoods of these things happening quickly depends on lots of other processes kicking in. And of course, I haven't touched on any of these because I'm really running out of time. So let me just conclude. So should we prepare for a transition? Is there something imminent here that we have to take seriously? And of course, you know, even at the end of my talk, I have to say it will take some time. It will not happen like tomorrow. But because, you know, the analysis that we did, they mostly relate to the wastewater part, but not to the urban drainage part. And of course, you can always say, well, you need a sewer mostly for the urban drainage, and then we just clean the water at the end. But let's say if we can decouple the wastewater treatment from the urban drainage, we can also deal more creatively with the urban drainage. And so totally new developments become possible. I guess a more severe argument is that the sector is really not very innovative and rather risk averse. So you don't have the high techies that go into urban water management yet. This could perhaps change soon. And so people are rather reluctant. So, oh, no, let's not change anything because we could run into some risks. And transition processes will take a long time, 2 to 4 decades anyways. So let's say it's nothing that we should be bothered about immediately, you know? However, I guess it would be still too early to relax because on the one hand side, we know that the land scrape pressure are likely to increase in the coming decades. You know, the West Coast experienced the fires, you know, you have floods and droughts and everything, which will really call into question the operating conditions of the urban water management system as we know it. A second major argument is, you know, it doesn't have to come from within the urban water management sector and industry itself, the transformation, but they might also just invade from other sectors. And a very illustrative example is that the camera industry, the photo camera industry, did not die out because people stopped to take pictures, quite the opposite, but because it was integrated in some more interesting item, namely the smartphones. And the smartphones got so good that there was no need, or only for hobbyists and artists, etc. You need still cameras. But let's say that the market just imploded in a very, very short time. And none of the camera companies saw that coming early enough. I guess what I try to show here, or at least lay out some arguments, is that this transformation can happen very rapidly once conditions are suitable. So it's not, don't believe that this is sort of a smooth substitution process, but if the thing starts to burn, it will burn very quickly. And now you say, well, but I was talking about 2 to 4 decades. Of course, it's not quick. You have to understand what quick is in such a sector. The relevant factor is not the absolute time, but the relative time to react, which means if you have an industry where your infrastructure has a lifetime of 80 years and a disruptive development could happen in 10 years' time, then after 10 years, you could be confronted with sunk costs and stranded investments for another 70 years. So if you want to change course, you have to change course in the planning today, trying to anticipate what could happen in 10 or 20 years. So let me conclude. I guess still the socio-technical transitions perspective is relevant already today. And I guess it would be good for engineering students in particular to get exposed to these sort of arguments. And we had just a very recent paper where we laid out some of the core research questions, both on the sides of engineering and the social sciences in the journal Environmental Science and Technology, which some of you might know as well. Thanks a lot. I overtook only by perhaps 5 or 10 minutes. I hope you apologize.
Fantastic. Thank you so much, Dr. Truffer, for that. I'm going to hand it over to Fuhar to run some questions. We're getting a ton of